Video 4, and what we're going to do is just look at gases from a kinetic molecular theory. A couple of things you already know about gases, but just to kind of formally review, they have an indefinite shape, which means obviously their shape can change. They have an indefinite volume. You can make them be bigger or smaller. And part of that is that they're very easily compressible. And all of this relates back to the fact that these particles are very, very far apart. So when you look comparatively at solids and liquids, their molecules are touching. They're right on top of each other. Gas molecules are not like that. When we're looking at kinetic molecular theory, what we consider is that basically, that's misspelled. Let me fix that. What we're looking at here is that they are going to be spheres, and they're very small. So for most situations, it's almost like we can ignore their volume because it's so insignificant. And when you have a gas, there is space between it. So remember, refer back to that diagram. You really want to be able to visualize these. With a gas, there's actually space between them. You can literally move stuff. So it's kind of interesting to think about that when you take a deep breath, most of what you breathe in is nothing. Like most of what you're breathing in is empty space. And it's an unusual thing to think about because you don't usually visualize things that way. One thing that they say is that because the gas molecules are really far apart, there's no attraction, or what we usually say in chemistry is that this leads to very few or little intermolecular forces. And intermolecular forces are just forces between molecules. So inter is between, and molecular just means molecules. So what we're saying is basically there's not attractions. Because of this, the particles really act independently. They don't know that other gas molecules exist. And gas molecules have the most energy, so they are the most rapid. They're in constant motion, and it is random. Random is actually kind of important because it'd be really unfortunate if all the oxygen molecules decided to leave your bedroom or your classroom or whatever. So the random thing's actually an important thing. Because of this, because they don't have attractions, because they act independently, and because they are in this constant motion, this is why the gas molecules or gases fill their containers. This is why their volumes can change. This is why they take the shape of their container. So understanding why a gas acts the way it is explains and helps us to kind of see, how they behave, why they behave. I mean, you all know that gases can be compressed, but it's good to understand why. On the flip side, it also means that gas particles can spread out. So they're not necessarily attracted to each other, which means they can move in any direction. And this is called diffusion. This is if you ever wear perfume or cologne, this is why you're wearing it. Perfume or cologne is naturally evaporates from your skin, and it diffuses through the air. And you're wearing it because you want people to smell you and smell good. So you want gas diffusion to occur. And there's actually a big science to perfumes and colognes because you have to use the right mix of volatile versus non-volatile things. Because if you put your perfume on and it all evaporates off of you in 10 minutes, well, that's not a very good perfume. But you don't want it to be so non-volatile that it never evaporates and then no one ever smells it. So you can be a perfume chemist in Paris, maybe. And then also, the last thing on this slide is particles are going to travel in a straight line unless they collide. So particles don't say, I want to turn the corner because it'd be fun over there. They just go and hit something and then bounce off in another direction. When particles collide, what KMT, or kinetic molecular theory, says is that it's perfectly elastic. So this is not a car crash. This is like bumper cars. They just bounce off each other. This is not where, they crash and collide and it's bad. When you have an elastic collision, you're not losing kinetic energy. So basically, any energy that is moved is just transferred from one thing to another. A big rule in chemistry is that energy is conserved, and in an elastic collision, total kinetic energy is conserved, but it can be transferred easily. When you have collisions of gas molecules, what happens is they exert a force. And the force that we talk about is actually pressure. So you guys know, there's different pressures and, that kind of stuff. Not the pressure from school, but gas pressure. And the formal thing here of gas pressure is that it is a force exerted by a gas per unit of surface area of container. So the simple thing is how many collisions are hitting in a given area. If I poke you once, every hour, it's not much force. If I poke you like 10 times a minute, you get more force. And that's what they're looking at with gas pressure. How many collisions are there and what kind of force do they have? And then last thing for this section is the phase changes, and we talked about these a little bit. If you're going from a gas to a liquid, we said it was condensation. What's happening here is the particles are slowing down, they're going to release energy, and the particles themselves are going to have less kinetic energy. Gas to a solid, we said before, was how the snow forms, the deposition, and here the particles on, this should say average, I apologize, are drastically slowing down. So this is that giant one, and you can see here, here's condensation, this little thing, here's deposition, so it's a much larger jump, and in both of these situations, heat is being released, because the particles are slowing down, they're not moving as fast. And that's it for video 4.